Hello and welcome back. This is Chapter 4 out of the Conceptual Physical Science book, 5th edition by Hewitt. And this is Chapter 4, Gravity, Projectiles, and Satellites. So in this lecture we're going to help you understand the universal law of gravity, taken into Newton's 3 laws and into a bigger law, his inverse square law of gravity and distance, weight and weightlessness, universal gravitation, projectile motion, fast-moving projectiles or satellites, circular satellite orbits, elliptical orbits, and escape speed. So Newton was famous for the falling apple out of a tree, and so Newton was not the first to discover gravity, but he was the first to discover that gravity is universal. So the legend was that Newton was sitting under an apple tree. He realized the force between the Earth and the apple is the same as between the moons and the planets and everything else. In the ancient times, Aristotle and others believed that stars, planets, and the moon moved in defined circles, free from the forces of the Earth, and they called these God paths, defined circles. Okay, so the fact of the falling moon, we know that the moon falls around the Earth in the sense that it falls beneath a straight line if it were to follow if no force acted upon it. The moon maintains a tangential velocity, which means perpendicular to its orbit, and that ensures a circular motion around and around the Earth rather than into it. And so this is similar to the paths of the planets around the sun. So here is Newton's law of universal gravitation. It states that every body in the universe attracts every other body with a mutually attracting force, and has an equation attached to it, which I'll describe to you, but not have asked you to memorize it. It says that for two bodies, this force is directly proportional to the product of their masses, the masses combined, and inversely proportional to the square of the distance separating them. So you see in the equation here, force is equal to this constant. We call it big G now, the big universal constant for gravity. We have a mass of two different objects, and they are inversely proportional, meaning 1 over d squared. Distance is d. So if you have two masses, if you double the distance between them, then you're going to go by a factor of 4 less force. So if you double the distance, 2 squared is 4, that means 4 times less force. So Newton discovered that the gravity is universal and that every mass pulls on every other mass. Okay, so the greater the two masses, the greater the force between them, and the greater the distance separating d, the weaker the force of attraction, the weaker as the inverse square of the distance between their centers. Very important. Let me see that here. So the greater the distance from Earth, the less gravity force on that object. No matter how great the distance, gravity approaches but never reaches 0. So here we see, double the distance, you're 4 times less of a force. If you are 3 times distant, then you are 9 times less force. And in this big equation, the big letter G is just a constant of Newton's law of gravitation. It's a very small number. It's in newtons, by the way, and it's this small number with a bunch of units attached to it here, so that the mathematics come out nicely for us in the end. So let's take a look now at weight and being weightless. Weight is the force exerted against a supporting floor or weighting scale. So let's say you're in an elevator or you're on the ground and you're standing on a scale. That's your weight. It depends on both your mass and the gravity field you are in. Weightlessness is a condition where a support force is lacking. You're in free fall, for example. And so here we are, you have an astronaut floating around space. They are in free fall around the Earth, and so they have that weightlessness experience. If you're in an elevator and you're standing on the ground floor, you have a normal weight. If it's going up, you're going to have more force pushing on that scale, so you have a more than normal weight. If it's going down, you have a less than normal weight. And if that cable snaps, you have zero weight and you're in trouble. Okay, projectile motion. A projectile is any object that moves through the air or through space under the influence of gravity. And typically projectiles move in a parabola, which is almost like an arched or curved shape. An example would be a stone thrown horizontally curves downward due to gravity. And so this is a result of constant motion horizontally and accelerated motion vertically up and down. And so the parabola here, you see that the vertical component changes with time. The horizontal component remains constant. Now, what is the best angle at which to throw a projectile? It turns out 45 degrees will achieve the greatest distance allowed under that throw. The higher the angle, the higher it'll go, but less distance. And so we also can include air resistance for this. And so with air resistance, both the range and the altitude are decreased. If you are in space with a projectile without air resistance, then the speed loss going up is the same as the speed gained when coming down. With fast-moving projectiles, like satellites in orbit, a satellite is any projectile moving fast enough to fall continually around the Earth. And to become an Earth satellite, the projectile horizontal velocity must be great enough for its trajectory to match Earth's curvature. And so Earth drops off about 5 meters for every 8,000 meters tangent, and that's perpendicular to the surface. So to orbit the Earth, a projectile must travel 8,000 meters in the time it takes to fall 5 meters. And so in a circular orbit, what we have here is a rocket fired vertically and then tipped. Once above the atmosphere, then the rocket's aimed horizontally. The speed of the rocket states that the payload must be 8 kilometers per second to fall around the Earth and become an Earth satellite, or 17,500 miles per hour for a spacecraft like a space shuttle or the SpaceX spacecrafts. And now positioning is very important because beyond Earth's atmosphere, where the air resistance is almost absent, we have this circular orbit happening. In an ellipse, though, like planetary orbits, this is an oval path, like egg-shaped, followed by a satellite. This is a closed-in path taken by a point in which there are 2 focus points you could travel through. And you see in the diagram down here 2 focal points by these push pins and a string attached with the pin drawing out the ellipse. And for planetary orbits, the first focus point, is that of the Sun, creating that. And so the speed of satellites vary in elliptical orbits. When they're close to the Sun, the planet will move faster. And on the other side of the Sun, they will move slower. And these are Kepler's 3 laws of planetary motion. Now, when we were going to the Moon, we had to escape the Earth's velocity. And so it turns out that you have to go faster to do that. It turns out to be about 11.2 kilometers per second from Earth's surface, about 6.5 miles per second, or about 25,000 miles per hour to escape Earth's gravity. And finally, the first probe to escape the solar system was Pioneer 10, launched from Earth in 1972, and the probe was directed into the path of the oncoming planet Jupiter. That's it for Chapter 4.